Okay, let's get started. So, for the second and last talk of the session, I'd like to introduce Simon Peyton Jones, who will tell us about typing application spines.
Okay, good. I need a microphone, but then I'll wander around. Because otherwise people online won't hear. Okay, so I'm giving two talks today, and both are trying to distill folklore out of the literature, and particularly out of implementations, into a sort of digestible form that you can make use of in your type checkers. But we're a kind of sad collection of people who thinks that type checking and type inference is really cool, right? But we're all in a room together, so let's share the love. And so this would be nice if we asked questions and made comments as we went along. We will fit in 30 minutes somehow. But so in a sense, I'm not going to tell you anything new, but I'm going to try to extract lessons that I've gotten from 30 years of trying to write type inference algorithms for GHC in the hope that they may have some resonance for you. Okay, so this talk is about applications, type checking applications. What's more fundamental to functional programming than this? So here's the lovely typing rule that we all know and love, right? And it deals with binary applications. Just apply a function to an argument. And it's sort of simple and beautiful and elegant, and it deals nicely with currying, and it doesn't have any dots in it, all very nice, right? So, so I'm going to focus on this, this problem. I'm going to show you a few, whenever I show sort of typeset rules, they're coming mainly from this paper, readily available on my homepage, which kind of both has lots of typing rules, but also it has an implementation, executable implementation right there in the paper. So it's good, it's very concrete. So the first thing I want to cover is, because it's sort of a precursor for everything that goes on, is a bit about bidirectional type checking and higher rank types. Many of you will know this well. In fact, bidirectional type checking is such a piece of folklore and such a well-known idea that nobody is prepared to admit that they invented it. Neil was just telling me he asked Thierry Cocon and Benjamin Pierce and John Reynolds. None of them would admit to inventing it, but totally useful. So what's the problem? Well, if you look at this application here, what are we going to do when we type the application? The obvious thing to do is to say, find the type of the function and find the type of the argument to check they're compatible, right? Infer both. But that doesn't work very well when you've got a higher rank function like this. So here's f, which takes an argument that itself is a function type, whose argument itself is a polymorphic function. A little bit strange, but Haskell programmers are very strange people. They do this all the time. So in a call of f, right, I'm going to call f on a lambda. Right? So here, this arrow type is going to be the type of f's argument, and I'm calling g at type int and type bool. So g had better be polymorphic, and we have enough clues to work that out, because we know that f is, we know the type of s argument. We can push that into the lambda, and so determine that g has this polytype for all a to n core. Okay? Simple. I mean, everyone can do this in their heads, right? If it's obvious to us, it should be obvious to a type checker. So the very good, well-known idea is to use bidirectional type checking, which we tend to notate by saying, well, in some environment, this term t has type row, and this little delta can either be up arrow for inference or down arrow for checking. The idea is, which direction is the type flowing? Down arrow means that row is an input, right? I'm pushing it down into the term, and up arrow means that I should think of row as an output, that is, I infer the type of the term. So far, so good? Okay? Now, let's see, and that leads us to, like in this practical type inference paper, we actually have two type checking algorithms, one for inference and one for checking. And the inference one says, give me a term and I'll give you a type. So this TC is the type checking monad. I'll say a bit more about that later. And the checking one takes a term and a type and produces it just produces we just type check it in this monad. Okay? So how's it good? Easy enough. What are these row types? Well, so we have to be a bit careful with where the quantifiers are when we're playing this kind of game with higher rank types. So sigma types and phi types are going to be ones with quantifiers at the top. So here are the foralls, right? So we can have an arbitrary number of foralls, and then we end up in a row. And what happens when we get a row? Well, we can have arrows and lists and so forth. We can have monotypes that are just no quantifiers anywhere in a tau. So tau you should think of as being some arbitrary type but with no foralls in it. Or it can be a type variable, a tau, or, yeah, okay, we good? You can ignore the kappa for now. Okay, so that's what rows are. So now we can answer this question about, oh, now how does bidirectional type checking play into this? Well, when we are looking at lambdas, we split into two rules, one for inference and one for checking. So for inference, what happens, we say, well, we don't know what type X has, so we're going to give it a monotype, right, because we can infer monotypes. That's standard Hindley-Milner kind of type inference. So we'll just, out of thin air, this isn't an algorithm yet, we make up out of thin air tau, but we're allowed to make up taus, right? I'm not going to explain very much about that, because I think most of you will know. Out of thin air, we make up a tau. That will be, in implementation terms, a unification variable. But when we're checking, well, we know when we're pushing down a type, we've got the type of the argument, and moreover, it can be a sigma type with quantifiers at the top. So we can push that down into the term T with an auxiliary judgment that is going to end up scholomizing this sigma type. I haven't written that out explicitly. Okay? So the important thing is that some rules are sort of polymorphic in the direction, but lambda is definitely not. And that's the key to making these higher rank types play out. It's just one way in which bidirectional type checking is a win. Okay. Now, so instead of, let's see. So now in implementation terms, I said we split into these two, and that's a bit of a pity. All right, because it looks as if you write two whole algorithms, right? That wouldn't be terrible. And expr, the expressions of the language, that might be a large type, so we don't really want to duplicate all that. So a standard enough idea is to say, well, maybe we could save a lot of work when we are inferring. Right? Maybe instead we could just make up a fresh type variable, a unification variable, and check that the term has that type. Okay, let me just say it once again to make sure you got it. When we want to infer the type of an expression, maybe we could cons up a fresh unification variable and check that the term has that type. And I've written out the code here. Make up alpha, a fresh unification variable, and call check. Easy enough, right? And so now TC infer is just a little wrapper around TC check who does all the heavy lifting. Okay. Now what's the problem with this? The problem with this is that these unification variables they are variables, I call them meta-type variables often because they are a variable that stands for a type that we don't yet know. So I'm getting a bit more algorithmic here. But key point, the type that we don't yet know must be a monotype. These types that we develop incrementally by unification are always monotypes. That's the rock to which I cling. Maybe you can do better, but that's a fundamental principle of GHC's thing. So here, therefore, I'd be checking that E has some monotype, so I couldn't possibly infer a polytype. I could never get this term, for example. I'm being a bit informal here. If I called infer on a term that had an explicitly annotated lambda, I'm jolly well expecting to get, as a result, that the type of that term is, for all A to A to bool, in this case. But I could never get that because that isn't the monotype, okay? So, problem, easy solution. And so here, this is a takeaway idea. I'm sure everybody implements this, right? But GHC certainly does and has done for 20 years. But it's a very good idea and it's a simple one. Just make your main type checker take not a type, but one of these expected things. And an expected thing is either I'm checking that you are that thing, or else I'm inferring, and now I'm going to have something that's very like a unification variable. Just a reference cell that I'm going to fill in. The idea is that TC, when he's given an infer, is going to fill in that reference with the inferred type. Simple enough. So it's very like a unification variable, but this guy can be filled in with a polytype. And that's not immediately obvious from what I've shown you so far, but it works out very smoothly and very fine. Okay, so it's just an idea that I suggest you take away. Very, very simple, easy to implement, works really well. Okay? Nobody is, oh yes, Garrett, thank you.
So is a TCRF different from a unification variable in that it's sort of, you're only matching, you're never unifying, you sort of know how it flows?
No, how is this different from a unification variable? Principally that you could infer it with a polytype, right? but it's not a first-class thing. The only place this goes is in expected. It can be pushed down. It never lands up in the middle of a type or anything like that. No, no. It's just, think of it, it's like a var parameter to a Pascal procedure, right? It just says, by the way, when TC of infer blah has finished, blah should be filled in. That's the invariant, okay? So everybody must make sure that's the case. Now, there is a bit of fancy footwork when you come to things like case expressions. So here again, I'm being a bit informal. Supposing I call TC, the type checker, on a case expression, well, I'm going to end up checking that E1 has type R. Oh, I should have put infer R here, sorry. I'm going to check that T1, I need to infer the type of E1 and I need to infer the type of E2. So can they both update this funny reference thing with perhaps different sigma types? Oh. But in fact, this is easy to get around. We just, at the cost of making the type system less expressive, but that's fine, right? It's a type system we're defining. If there's a multi-branch case, we just insist that the result is a monotype, right? So operationally, the moment you try to update this thing, you find it already has a value, you say, okay, let's make it a monotype, which means unify it with a unification variable. It's easy. So there's a little bit of footwork there that I just don't want you to think it's trivial. You have to be a little careful here, but it all works out. Yeah, Richard.
I thought we did that ahead of time.
No, we don't do it ahead of time. In fact, as it turns out nowadays, it's sort of on the fly, for what it's worth. Maybe it'd be better to do it ahead of time. Now, okay, so where are we? Good. Okay, we're 10 minutes in, and so we have 20 minutes for the title of the talk. The title of the talk was about type checking application spines, right? So the first thing I want to do is to say, what is not good enough? So now we sort of got to the boundary of the practical type inference paper. In fact, I don't think this idea was in the practical type inference paper, so we got a little bit beyond there. But we still haven't got, no cigar yet. Why no cigar? So I'm going to show you 4 sort of inadequacies for what we got so far. One is error messages. Right? So if you've got, something like this and you pass a Boolean as the second argument to F, really you'd like an error message to say, oh, you would like it to say that the second argument to F should be rather than the third, but otherwise you'd like an error message like this. But the danger is that if you don't pay some attention, you may just say, oh, I can't unify int with bool, go figure, right? But to say, in the second argument or the third argument, we've got to have a notion of that there is an F at the head of this application and that we're in the second argument, right? So we used to have some ad hoc stuff for that, but this talk is about making it a bit more systematic. So that's number one. Number two is this. JHC these days has something called visible type application, which many languages have, right? And what many, let's say, sort of statically typed sophisticated languages have. So what does that mean? Well, if I've got this function, polymorphic function reverse, I can call it just passing it, some list argument, but I can also explicitly give the type that instantiates the polymorphic variable A here. So this says, in this call of reverse, please instantiate A with int. So x's had better be an int. Now, what's the problem with that? Well, if you think about the binary application thing, when I infer the type of the function, what do I get? Let's look back. Where's my inference judgment? I infer the type of the function and I get a row. And does a row have quantifiers at the top? No. So how can I instantiate them? Right? And it's very reasonable because if I've got a function with some quantifiers and then some arguments, it might be we somehow need to get a sigma type back here. And one possibility is you could say, oh, well, fine. Look, if I have one of these at things, I'll just generalize the type. I know how to do that. But then you think, but it might be quantified over several type variables, and then in which order do you generalize them? So now you start tearing your hair out. GHC's story, in papers, I think it was your paper that first described this visible type application game, is just to say, no, we'll only do this when there is a visible function at the front, so we know its type. It was declared by the programmer, and we know the order of the quantifiers. So, something about knowing the function at the front is going to play a role here. Okay? That was number two. Number three, impredicative types. So here's a little cottage industry of papers about trying to figure out how we could instantiate reverse, a polymorphic function, at, but instantiating A, not with int, but with the type for all B, B arrow B. Whoa. Okay, because now, this argument here is a list of polymorphic functions, so I must instantiate A with this polytype. Okay? So how are we to do that? That's called impredicative instantiation. So cue long sequences of many papers that try to do this, including, embarrassing to say, I think at least 3, which included me as a co-author, all of which turned out to be bad ideas. But finally, this one turns out to be a good idea. Now, how is it a good idea? Well, the idea is the way that quick look works is it takes a look at, if you look at this thing, you think, well, reverse applied to Wise. Wise has type, list of for all B, B arrow B. Guys, it's so obvious. So obvious. The only thing we can instantiate A is this. Right? If it's obvious to us, it ought to be obvious to a compiler. And the idea of this whole paper is to make, to formalize what it means to be obvious, right? To catch the obvious cases. So you could go read that paper. But that was the third reason. But it required us to know this sort of known type reverse at the front to figure out the instantiation. Yes,
Good
DDA.
to ask question during, or do you want to wait for the end?
Is it ask question now.
When you say it's so obvious, you could instantiate YS as well. So I think you cheat when you say.
Oh, wait. I'm saying that Wise, we know its type for some reason.
Yeah, but it can be. Oh, it's in the list.
It's somehow Wise is a term variable that happens to be in the environment, right? Maybe it has a declared type.
Okay, I missed the list because I read in Camel when I would just say.
Sorry about that. Okay, anyone else? This, by the way, is point 3. Joachim.
Right, so this row type, so suppose I'm checking like an if statement.
Louder?
Yeah. So suppose I'm checking an if statement.
Yes.
And I pass in a variable that has this row type. So I get out of the then branch, I get that it should be an int, and then out of the else branch, I get that it should be a bool, right? But it's sort of while I'm checking the else branch, it's I try to update this reference, right? I find out it's a bool, so I throw an error message, and the error message says this variable should be an integer, right? When really what I meant was this if statement is not typable.
Right, so you're saying that in an example like this, you're backing up to an earlier slide, right? So in an example like this, well, I'm trying to, if E1 and E2 have different types, I don't really want to complain about E2 or about E1. I want to somehow complain about the whole thing. Yes. That's absolutely true, and I think so I've not put a lot of effort into trying to improve that error message. But I think this setup might make it more feasible, but I don't think we do a very good job there. I think today we'll just we'll complain about E2 for what it's worth. Sorry. We should do better.
So a few slides ago, you were telling us that it's a bad idea to try to pretend that the two cases of bidirectional type checking and inference are the same thing because we can't encode type checking, this failure, we can't encode it as checking against a fresh variable.
Yes.
Because of this thing that the meta variables stand for monotypes.
Yes.
But now you're introducing impredicative instantiation, so.
Yes.
Does this idea start working again?
So the whole point of the quick look paper is to say we can get this behavior without having unification variables standing for polytypes. I'll give you a quick clue in a second about how that works, but that is the key payload of this paper.
Okay.
Yeah.
So
because the unification variables that flow around and live in the middle of the types and have a long lifetime and get solved incrementally, those are still monotypes. Making them be polytypes is something that people have tried really hard to do but never found a good way to do. Okay. What else? Good. This is good. Right. Into the bowels of type inference. Okay. Let's see. So, what was the last thing? Fourth point. Right? Fourth sort of trickiness about just dealing with binary applications only is when we come to a function like this. So, and this is, remember, Haskell is gradually pushing in the direction of, we have Agda envy and we have Idris envy. Right? We're driven by Richard and Stephanie. We're creeping towards dependently typed programming. And one of the things we want to creep towards is to say, well, in a function like this, for all a, this is a type class constraint, size they double arrow int. Well, since there is no a to the right-hand side of the double arrow, really every call of sizeof must specify the type at which we're instantiating sizeof, right? So every call of sizeof would have to go sizeof at blah, right? And it would be quite nice to make that explicitly. So we'd like to give sizeof the type for all a, and in Haskell now we're notating this for all a arrow rather than for all a dot. And the for all a arrow means that every call must look like sizeof, and then you just give a type, no @ sign, and it's compulsory to give a type. Right, it's not optional, because if you leave this out, the complaint would be obscure, be something about ambiguous sized a constraint. It's all very obscure. Whereas this, it's compulsory. Yeah? But now you've got functions with different shaped quantifiers, right? And so that's going to make this binary instantiation, the binary application game, fall apart as well, for what it's worth. So it's 4 things. So 4 little straws in the wind. So the very simple solution. So finally, the payload of the talk is something that which is very easy to understand and intuitive, but just we fought against for ages because binary application just seems like, so simple, so elegant, but once you do this one thing, everything else becomes easy. And then you're, okay, so what's the one thing? Well, it's simply to treat applications as a whole. So what do we mean? An expression is, well, it can be a lambda, I've left out let and case and all the other many cases. Well, it can be an application. And what do I mean by an application? Some head h applied to one or more arguments. Well, actually 0 or more arguments. N is just bigger. So even variables show up in this production. And what's a head h? A head h can either be just a simple variable, that is the function at the head, or it can be an expression with a type signature, an explicit user-supplied type signature, or it can be, well, an arbitrary expression, but preferably not itself, that this guy should not really be an application, because otherwise you could have had a longer h here. So you could make the syntax a bit more complicated to formalize this, but I've just put not an application here, right? So this E is not going to be one of these h guys. Okay? They're pretty simple. That's the syntax of expressions. And once you've got that syntax of expressions, now we can say, well, in the common case, very commonly, in like 99% of all applications, the h thing turns out to be just a variable. There's a function at the head of most application chains. And when it is a variable, we know its polytype. It's in the type environment. Because remember, gamma has bindings of variables to their polytypes with all their quantifiers, gloriously decorating them, right? This expression with sigma, that's just a kind of, what's the word? It's not common to see expression : type applied to things, but it's kind of simple and uniform to put it there because, again, this expression, we know the polytype of its type, right? Namely, sigma itself. That's easy. But then we can bail out. If the h is some arbitrary other expression, say a case expression, then we could just give up and say, fine, we'll just do what we did before, but we won't get fancy polytypes out of it, we'll just get a row. Okay? But this is not very common, and I don't think many programmers, nobody's ever complained that they don't get some fancy polytype out of this that can then be impredicatively instantiated, right? It's just not what people are worrying about. Okay? So far so good? So pretty, very simple, really. So now, once you've got that idea, how can we, beg your pardon?
No, I want to ask a question.
Oh,
Not as a
right,
session chair, as an audience
I've got
member.
7 minutes.
No, sorry. Sorry, I was just looking at this case expression, and you just mentioned how in GHC you're moving more and more towards dependent types. And I'm thinking that actually this pattern is very common in dependent types, where the dependent type of the case is quite different than the types of the branches.
Oh, okay. So if you want,
I wonder if you thought of that.
No, if you want the dependent, so if you really want to write this, and you want it to have some, sophisticated type that gets informed, then you will have to put a type signature after it, right? Or give it a name and give that a type signature, one or the other. But what you won't get out of the system that I'm describing, at least, is it'll just sort of magically combine and create strange polytypes out of here, and no. So, sorry.
Okay,
Yeah. But there's an escape hatch that doesn't seem too unreasonable. Okay, anyone else? Okay, so then, but I want to stress, this is not just an implementation technique. This affects what programs are typable. Right, so we've got to write typing judgments for it. So this is the typing judgment for applications. So let me just walk through it, because this does have a little bit of technical content and is worth grappling with a bit. But once you sort of internalize the way application works, everything else becomes easy. It's so good. So how do we type check? And this is going to work for any delta, right? Up and down, checking and inference. An application applied to 0 or more arguments. Well, the first thing we're going to do is to infer the type of the head thing. Now, H. How do we do that? Well, here it is. Very simple judgment, actually, because, and notice it returns a sigma. Ooh, the power of saying sigma rather than rho. Right? As, you know, tell this to an ordinary room of people and they say, yeah, whatever, right? But to you guys, you think, oh, yes. Okay, so why does it? Well, remember, there are only 3 forms of H. If it's a variable, just look it up in the environment, and we got a sigma there, because gamma contains bindings of variables to their polytypes. If it's an expression with a type signature, we got the sigma right there in the term. The user wrote it. And if it's anything else, well, just bail out into ordinary old inference for E, and then you only get a row back. But every row is a sigma, just with no quantifiers. Okay? So H is very simple. Now what else happens? Oh, so now we know the type of the function. Now we have to instantiate that type, because it's got some foralls floating about, and we instantiate it. So this is a complicated judgment. It says you should think of it, input is the sigma type of the function, and the list of arguments pi, and I'm going to get out the instantiated argument types phi, and the final result row at the end of, in the corner, right? So this guy is just saying, take sigma and strip off his foralls and take his arrows apart, as many arrows as are necessary to satisfy the pi, and give me back 1 phi for each of the pi's and a result, okay? Now then, now we come back to your question about unification variables and so forth. So this says instantiate the function with fresh instantiation variables. So instantiation variables have a very short life, right? Instantiation variables are born here, right? And then at this point, this is a funny line. What does this say? It says take the free instantiation variables of phi and rho, and take the free instantiation variables here, and for each of them choose a monotype. Now, why is there this fancy footwork with instantiation variables? It's because the quick look algorithm for impredicative instantiation is actually going to figure out polymorphic instantiations for some of these instantiation variables. But so while you're not thinking about quick look, you can just imagine inventing taus here, but there's just a little intermediate step. So this rule is built to scale to quick look. Right, and once we got that, now we can check, down arrow, that each of the arguments pi, oh dear, E is the value arguments. Each of the argument has the type that you expected, that you got out of here. And finally, you have to check that the result type row here matches up with rho R. Easy, right? So then all of the fancy footwork occurs in the instantiation judgment. What does it do? Well, it takes this type and these arguments, and it gives you the argument types phi and the result type rho, and it takes care of all these required arguments and visible. There's quite a lot of moving parts in this guy, but all of the things that I told you were tricky are all embodied in this instantiation judgment that I'm not going to work out. I'm just showing you this slide to say, look, it fits on one page, all right? And if I just take one example, what's this? This is a visible type application. So we got a forall, and the first argument is an explicit sigma. I could have written @ sigma there. It's an explicit user-supplied type argument. Well, then what do? Well, of course, I just instantiate that A with this sigma. that was what the visible type application said. Easy, right? Boom. So you can read the paper. This is all in the quick look paper. But it scales nicely, that's the point. So what I want to say by way of finishing then, that treating function applications as a whole is a piece of folklore that many of us in this room will have found our way to implementing it. But it's very, very valuable. It exploits the wildly common case of having a function at the head. It degrades nicely in other cases. And moreover, as I discovered 5 minutes before giving the talk, by appeal to higher authority, it is in fact not just a random hack for a poor, sad compiler writer, but actually a deeply principled process. So I appeal to Neil now to explain what I mean by that.
Okay, when you look at polarized type theories and give them a syntax, then you discover first that NRA functions are actually very natural, which is why we have these top-level clausal definitions, and sort of dually to that, like. When you have like a negative type or a function type, you naturally want to supply it with a whole list of arguments at once, and the semantics of this like works out very nicely with call by push value as well. So a good paper to look at this is Arnaud Spivak's A Dissection of L.
Okay, thank you. You may say that, I couldn't possibly comment, but I'm very glad to hear that this egregious hack actually has a deep logical foundations. But really the conclusion is, the takeaway is, look, you should just do this, right? It's a straight win on every dimension. And anybody who's writing a type checker should have a good reason for not doing this, I think. Good, thank you.
No, thank you. Thank you, next speaker. Okay, we're about out of time, so I'll ask for maybe one or two short, quick questions.
Yeah, so you didn't talk about how to implement the error reporting when we have a type error. I assume it's easy. Is it as easy as I think it is?
Yeah, the error behavior is pretty much as easy as you think it is, because like in this vector down arrow thing, we're making n calls to TC check, if you like, but we know for each of the n's we know what n is. So you can sort of say I'm now in the nth argument. That's really all. There's nothing more sophisticated than that.
So this was supposed to be the last question, but actually I have two. One is that the multi-application, if you let bound only some of the arguments, then now you have to do the application in 2 steps. So you're not stable by a transformation that let bound some arguments. This is more.
Oh, you mean if you picked out the prefix of the application and let bound that, you're completely not stable under that. That's true. Yeah.
And the other remark is that you said that unification variable should not be substituted by should only be substituted by monotypes. You said this like a key rule, and that's not the point. They can be substituted by polytypes, but those polytypes should not be used unless you know that they really have those polytypes.
Oh, so you're talking about MLF, really, aren't you?
Just Camel does that. So MLF does that as well, but Camel also does that.
Okay, so I need to understand that better. So I think, Didier, you're saying that I said the rock to which I cling is that unification variables are instantiated only by monotypes, right? And you're saying, actually, you can relax that under some circumstances.
Yes, this is what I'm saying.
I should understand that a bit better. Thank you.
Okay, let's continue the questions at lunch, and thank our speaker.
Lunch. Good.